Okay, we'll be dealing with complex numbers, and these come up sometimes when we're solving quadratics, and it happens when we're taking a square root. So sometimes we have a negative over on the side, and we take that square root, and I'm starting with -1 here. And this is actually, in math, it's an imaginary number. And it's not imaginary in the sense that it's not actually exist. It does exist. Like, here it is. It's square root of -1. So the definition of an imaginary number or a complex number is a number such that if I square it, I get -1. Now we know that most numbers, if we square it, like if I had -5 and I square it, I get +25. And if I have -1 and I square that, I get +1. So what we're saying that this I, or the letter I, if I square that, it's a number such that I do get a negative. So I squared is -1, and this is a definition that we're going to want to memorize because it's going to come up an awful lot. So I have over here the square root of -64, and normally, like earlier in math, you were told, well, we can't do this, but that's actually not true. We can do this. We're going to use this definition. So what we're going to do is we're going to say, well, this, and we don't have to write all this work. I'm not going to show you. First of all, I'm going to write square root of 64, and I'm going to take that negative and move it out here. So now I have square root of -1. Well, what is the square root of -1? Well, according to this definition, the square root of -1 is I. So I'm going to write that as I. And right here, square root of 64 is 8. So our answer for this is 8I. So we don't necessarily have to show all that work. We could just say, alright, we recognize this is the square root of a negative, therefore the square root of 81 is 9, and since it was negative, I'll have I as my imaginary component there. And the square root of 16, again, I'll just show that work one more time. So I have square root of 16, and I move that negative out, because if I multiply those, I get 16. The square root of 16 is 4, and root -1 is I. So again, before moving on, we need to memorize this because this is the whole definition of what an imaginary number is. It is a number such that when I square it, I get a negative. So that's not true of the real numbers, but it is true of the complex numbers. So let's try factoring now. So this is the difference of perfect squares, and it's called that because I have x squared here, and 64 is a perfect square because 8 times 8, 64, comes out perfect. So if I factor this, I get x, 8, 8. Now, in order to get this negative, one of these are negative and one of them is positive. And if I were to check this, I would get x squared plus 8x, -8x, -64. And then when I combine those, x squared minus 64. Now that was just my check to show that that's actually what it is. I don't need to actually do that. So when I factor all of these, they come out basically the same. And all I'm doing is taking the square root of 25, square root of 81. So pretty simple right there. So these, though, are the sum of perfect squares. And in algebra, when you went over this, you should have been told, well, we can't do this. We can never factor the sum of perfect squares. And again, that's not true in the real, or that's not true. True in the sense that I can't do it in the real numbers, but I can do it if I allow complex numbers. So what I'm going to do right here, before I go ahead and try this, is I'm going to say, well, this is x squared minus -64. Alright, so now I have it, the difference of perfect squares, and now I'll have x. Now remember, how did I get this 8? Well, I square rooted. So I have minus, plus, and what's the square root of -64? Well, 8i and 8i. Okay, so right here, x squared minus -25. So x. Now this is the difference of perfect squares, and the square root of 25 is -25 is 5i. X. And this time I'm just going to jump to it. 9i minus plus. And the reason I got that is I rewrote it as this. So the square root of negative 81, negative 9, and 9i. Okay, so sometimes we're asked to simplify, and we're going to want to make sure that we recognize this chart. We're going to want to have this memorized. It's not that difficult to do, so we started this. That's what we started with, and we said, well, I, the imaginary numbers, the number such that when I square it, I get negative 1. So these form the basis. So I cubed, and I'll do this work over here. I cubed I could rewrite as I squared times I. Well, what's I squared? Negative 1. And I have I. So negative I. And right here, I to the fourth. Well, I can rewrite that, I to the fourth, as I squared times I squared. And what's I squared? Negative 1 times negative 1. So what's negative 1 times negative 1? 1. So I to the fourth is 1. So sometimes we might have these higher powers of I, and we're going to want to figure out, well, we don't need this higher power of I. We can write it as something lower. So all I care about really is this power, this 80. And the highest power that I have here on my chart is 4. So all my combinations of i's go up to 4. So I'm going to use that largest combination, that 4, and I'm going to say divide by 4 right here. So I have 2, 8, 0, 20 times. So this came out perfectly. So what does this mean? I could split up this I to the 80 into I to the fourth times I to the fourth, and so on and so forth, 20 times exactly. Well, what is I to the fourth? 1. So 1. Now, they don't all come out quite like that. This one had a remainder 0. So, came out nice. So what about this one? Again, I'm going to try to get out all those I to the fourths. Why? Because I to the fourth is simply 1. So I'll divide this by 4. I have 1. So this is something that you do have to do by hand. 12. And this time I have a remainder. I have a remainder of 3. So what does this mean? Well, I have 13 I to the fourths. And then I have I to the third left over. So what's this equal? I to the third. Well, what's I to the third? Negative I. So this is our answer here. So again, we want to have this chart memorized. Okay, we have 31. So again, we'll divide by 4. So maybe a 7 here, and get 28. Subtract. So I have a remainder 3 again. So what's this mean? I have 7i to the fourths, and I have an I to the third left. So I to the third, which equals negative I. So I want to do one more that doesn't come out to either one of these. Let's try I to the, well, let's try I to the 10th. I to the 10th. So if I take that 10 and divide it by 4, 2 times, I have a remainder of 2. So what's that mean? I have I to the fourth, and then I have I squared left over. All I care about is that remainder, and that is negative 1 from our chart right here. So we're going to want to memorize that. But the biggest, most important thing in this chart is this definition right here, that I squared is negative 1. Okay, so we can simplify complex numbers pretty easily. So if I had 2x plus 5, and then I added 3x plus 8, we know that I would just combine my like terms. So 2 plus 3 is 5x, and 5 plus 8 is 13. I'll just add my like terms and then I'm done. So the same thing goes for complex numbers. So I have a 6 right here and a negative 8, so 6 minus 8 is negative 2. And then I have right here a 3i, and right here a negative 9i, so 3 minus 9, that's negative 6i. So, there's our answer. And we want to write our complex numbers in this form, a plus bi. We basically want the i's last, so we want this order. So this was out of order. So I have a minus here, so I want to distribute that minus and switch to plus, just like I would if it were just with x. Okay, so now I combine my like terms. 7 plus 5 is 12, and negative 2 plus 8 is 6i. So there's our answer. We just combine our like terms. So I'm multiplying. So remember, if I had like x squared times x cubed, I would add these. So x to the 5th, I don't need to write that out, but I add my exponents when I'm multiplying. I add them, and this is the reason why. So if I had like 2x times 5x, I would multiply the numbers in front, 10, and x times x, the exponents are 1, so I add those and get x squared. So right here, what do I get? Well, 5 times 9 is 45, and I times I is I squared. Now I don't want to leave that like that because I squared equals negative 1. So this equals negative 45. And I'm done. So I can distribute just like in real numbers. So I distribute that to negative 2i, and I get negative 8i, negative 2 times 4, and then negative 2 times 3 is negative 6, and I times I is I squared. And again, what is I squared? I squared is this negative 1. So this is negative 1 right here. So what's this change the 6 to? Negative 6 becomes 6. I'll write that first because I want to keep this form right here. So I get minus 8i right here. Copy that down. So that's that simplified. So this distributes just like if it was real numbers. So this 3 goes to both of these, and I get negative 15 plus 18i. And then this negative 4i, take the sign with it, goes to each of these. So I get plus 20i minus, now negative 4 times 6 is negative 24, and I times I is I squared. And I squared is negative 1. So what's that switch this to? Plus 24. I can combine those, and I get 38i. And right here I have negative 15. Alright, so I combine my like terms, and I get, looks like 9 plus 38i. I'm going to do one more real quick. We would get 10 minus 20i minus 2i, and then this last thing, negative times negative, positive, and then I times I squared, and I squared is negative 1. So I have negative 4 right there, negative 22i, 10. 10 minus 4 is 6, and minus 22i. Okay, so nearing the end right here. This is the last thing. Now, you should have learned in algebra, like if I had something like this, I can't leave a radical in the denominator. So I would do something called rationalize. So we need to rationalize these. We can't leave the I in the denominator because that's I is square root negative 1. So I would rationalize like this. Root 2 times root 2 is root 4. And then I can't multiply those, so I just write it like that. And the square root of 4 is 2. So this would be that simplified. So right here, I can't leave this I down there. So I is square root negative 1, so I'm going to multiply top and bottom by I. When I distribute, I'll get 6i minus 3i squared, and 2. I didn't need to take the 2, and then 2i squared. Well, what's I squared? That is negative 1. So I have negative 2 down there, and then this is negative 1, so that gives me a positive 3, and then I have my plus 6i. And then there's my simplified answer. Right here, now this is tricky. I can't just multiply by I. I need to use something called a conjugate. And a conjugate is basically the same thing but different in sign. So if I have like root 2 plus 5, the conjugate of that is root 2 minus 5. So if I had something like this, I have 3 plus 2i. The conjugate of that is 3 minus 2i. And when I multiply by conjugates, basically the radical goes away completely. So I'm going to multiply by the conjugate right here. So I distribute this 6, and I get 18 minus 12i all over. Now, if I do this, I will get 9 minus 6i, and then when I do the 2i, I get plus 6i, and then 2 times negative 2 is negative 4, and then I times I is I squared. I squared is negative 1, so I get a plus 4. See, these cancel, and I have a 9, so I get 13. So 13 down there. So this one, well, what's the conjugate of this? Well, 4 plus 5i. So now my multiplication will take a little bit longer, but it's still not too bad. 4 times 4 is 16, and then 4 times 5 is 20i, and then negative 20i, so that I thing should go away, and then minus 25i squared. This is negative 1, so that's going to be plus 25, and I have 16 right here, and 16 plus 25 looks like 41. See, I don't have a radical down there. Now the top, a little bit tricky. 5 times both of those. That's going to give me 20 plus 25i. And then I times both of those, plus 4i, and plus 5i squared. And again, see that I squared comes up an awful lot. That's negative 1. So I get 20 plus 29i. I added those. And then minus 5. Combine those, so I have 15 plus 29i all over 41. Okay, so hopefully you followed along with that. Last thing, just real quick, if this were to happen, so let's say I had 15 plus 20i all over, let's say, 10. So I need to make sure that I simplify this completely. So I look at all these numbers right here, and I see that I can divide them all by 5. So I do. So 15 divided 5 is 3, plus 20 divided 5 is 4, and 10 divided 5 is 2. And the reason that that works is because at the top I could factor out a 5, and at the bottom I could also factor out a 5. Factor out a 5, and then those cancel. So, we are done with complex numbers. Good luck on your practice problem.